Hello, let us continue our discussion on crystal vibrations. In this lecture, I would like to draw your attention to the case of diatomic bases. That means vibration in crystals of diatomic base. Bases contain two atoms. We will see at the end of the lecture that for crystals with a diatomic basis, for each polarization mode in a given direction of propagation of the vibration, the dispersion relationship between omega and k develops two branches, namely acoustical branch and optical branch. Let us assume the direction of propagation of the vibration, elastic vibration, or the direction of the wave vector is in such a way that the alternate plane contains single kind of atoms. That is, the atoms of mass m1 lie on one plane and atoms of mass m2 lie on the next plane. So, a single plane contains only one kind of atom. So, we will assume such a direction. Okay. Let me draw the figure here. So, here mass, this is one kind of mass and this is the next kind of mass. Okay, so the successive plane, sorry, alternate plane contain only one kind of atom. So this is the masses, this mass m1 and the mass m2. Here in this m1, m2 like that. And the displacement of the mass from its mean position is, this is represented by u. Okay, so let me put this as u, the nth plane of us, and this is the displacement vs. Okay, and this is the displacement of the first kind of atom, that is us plus 1. This is v s plus 1. Similarly, next plane, okay, s plus 2. This is v s minus 1, u s minus 1 like that. Okay. So these are the displacement. So we can represent with the displacement of first kind of atom is with the u and the displacement of the second kind of atom with the v. Let us imagine when the vibration propagates through the crystal, each planes of atom interact with the nearest neighboring planes. Okay. The equation of motion of an atom in the nth plane with the mass m1 is m1 d square us divided by dt square. So this is force on the nth plane with the mass as 1. First mass. So that is m1 d square us divided by dt square, which is the force, is equal to minus c us minus vs plus us minus vs minus 1. Okay. Here the one plane interacts with the only nearest neighboring planes. Okay, so for a plane there are two nearest neighboring planes. So therefore, if we write the equation of motion for the first kind of atom in the nth plane, so this is the equation. Here c is the force constant of the interaction. In both these interaction, both the interactions are identical. Therefore, the constant c is same for both the interaction. Okay. Similarly, the equation of motion of the second kind of atom in the nth plane, that is m2, mass of the second kind of atom, m2 d square vs divided by dt square is equal to minus c vs minus us plus 1 plus here vs minus us plus 1 minus c into vs minus us. So these are the equation. The first equation can be written as m1 d square us divided by dt square is equal to c times vs plus vs minus 1 minus 2 times us. Similarly, the second equation m2 d square vs divided by dt square is equal to c times us plus 1 plus us minus 2 vs. Okay, so let us put this equation number 1, this as equation number 2. The two equations, this equation have a traveling wave solution of the form us is equal to u exponential I s k. So us is equal to u exponential I k, and it has a time dependence in the form of exponential minus I omega t. And vs is equal to v exponential I s k a exponential minus I omega t. Okay. Here a is the repeat distance. It is the distance between the nearest identical planes. Okay, or it is called the repeat distance. Okay. Substituting the values in the above equation, these values in the above equation, we will get equation 1 as so this is the equation number 1. So you can simplify here u exponential I ska exponential minus I omega t is there. So here v exponential I ska exponential I minus I omega t. So this exponential I ska exponential minus I omega t is there in all these terms. So we can cancel all these factors, exponential I ska and exponential minus I omega t. So therefore it will become, this equation can be written as omega square m1 u is equal to c times v plus v exponential minus I k minus 2u. Okay, or once more we can simplify this thing as omega square m1 u is equal to c v into 1 plus e raised to minus I k minus 2c into u. So this is equation number 3. Similarly, if we substitute the value of this u and v in the equation number 2, m2 d square vs divided by dt square equal to c us plus 1 plus us minus 2 vs, we will get next equation as omega square m2v is equal to c into u 1 plus exponential I k minus 2c v. This is equation number 4. So we get two equations. If we rearrange this equation, we will get, we can write this, we can rearrange this equation once more as, so take the coefficients of u and v separately. So 2c minus omega square m1 u minus c into 1 plus exponential minus ika is equal to 0. Similarly, this can be written as minus c 1 plus exponential ika plus 2c minus omega square m2. Here u is there, here u is there, here v is equal to 0. So equation number, so let us, we can cancel this. This is equation number 3, this is equation number 4. Okay. These are homogeneous linear equations. They have solution only if the determinant of these coefficients of u and v vanishes. That is 2c minus omega square m1, here minus c 1 plus exponential minus ika minus c 1 plus exponential ika 2c minus omega square m2. So this determinant is 0, then these equations have a solution. Solving this determinant will get 4c square rearranging the coefficients. So m1 m2 omega raised to 4 So this is a equation, this is a quadratic equation in omega square. So therefore we get the solution omega square is equal to minus b plus or minus b square root of b square minus 4ac by 2a. So here 2c m1 plus m2 divided by m1 m2 plus or minus root of b square is 4c square m1 plus m2 divided by m1 m2 whole square minus 4, a is 1, c is into 2c square divided by m1 m2 1 minus cos k divided by 2. We can take 4c square m1 plus m2 divided by m1 m2 whole square from this square root, we can write omega square as 2c m1 plus m2. Now we can take the limiting cases of omega square, that is when Ka is very small. Okay, so therefore it will become, what is cos Ka? Cos Ka is equal to 1 minus x square by 2 factorial plus x raised to 4 by 4 factorial, etc. So here when Ka is very small, we can write this cos Ka is equal to 1 minus k square a square by 2 factorial. Okay, so this omega square is equal to using Taylor expansion, we can write this thing as 1 minus x whole raised to half. So that is 1 minus 1 by 2 1 minus nx. So it will be 1 minus 1 by 2 2m1 m2 divided by m1 plus m2 whole square 1 minus cos ka. So 1 minus cos ka is can be written as 1 minus of 1 minus k square a square by 2. So this will become k square a square by 2 divided by 2. Omega square, we have omega square is equal to 2c, either 2c m1 plus m2 divided by m1 m2 plus 2c m1 plus m2 divided by m1 m2. So since k square a square by 2, this k square a square is very small, we can write this thing as 1 minus some small quantity. So we can neglect this term in this. Okay, so therefore this will become, sorry, so we have a term in the denominator 2. Okay, so therefore you can write this thing as omega square 2c m1 plus m2 divided by m1 m2. Okay, or 2c, this can be written as 1 by m1 plus 1 by m2, 1 by m2 plus 1 by m1, or 1 by m1 plus 1 by m2. So this is the frequency, the square of the frequency for corresponding to this plus term. Okay, so this frequency is called optical branch. Okay, so this is a limiting case when Ka is tends to 0. That means when k tends to 0, A is the lattice parameter. Now we have the term corresponding to this negative, that is omega square is equal to 2c m1 plus m2 divided by m1 m2 into minus of minus will become plus, so into 1 by 2 m1 m2 divided by m1 plus m2 whole square k square a square by 2 all divided by 2. So this is c by 2. m1 plus m2 is there, m1 plus m2 whole square is there, m1 m2 get cancelled. So finally this k square a square divided by m1 plus m. Okay, so here we are not neglecting the final term, because when we neglect this, this will become 0. Okay, So omega square is equal to c by 2 k square a square divided by m1 plus m2. So since this is corresponding to the negative of this quantity, this is called uh, acoustical branch. Okay, so this is the acoustical model. We will be discussing about this nomenclature later. So for now, this omega square we have when k is very small, either 2c 1 by m1 plus 1 by m2 or c by 2 k square a square by m1 plus m2. So these are two different modes. Okay. So here from this it is very clear that omega is directly proportional to k. That means omega is linear function of the wave vector k. Okay. So at the low value of k, omega is directly proportional to k. Next case is when k is maximum, that means plus or minus pi. Okay, k is equal to plus or minus pi, or k is equal to plus or minus pi by a. Okay, so this is the boundary of the first Brillouin zone. Then what is omega square? Omega square is equal to, in this equation we can go to this equation. When Ka is pi, then cos Ka will become minus 1. So 1 minus minus 1. So this will be 1 minus 2m1 m2 divided by m1 plus m2 whole square into 2. So this will be 4m1 m2. So we can write this omega square expression once more here. Omega square is equal to 2c m1 plus m2 this m1 plus m2 whole square plus m2 whole square minus 4 m1 m2. So root of this quantity by 2. So this is m1 plus m2 whole square minus 4 m1 m2 is m1 minus m2 whole square. So this will be 2c m1 plus m2 m1 m2 plus or minus 2c m1 plus m2 divided by m1 m2 into m1 minus m2 whole square divided by m1 plus m2 whole square. So this will become root of that will become m1 minus m2 divided by m1 plus m. So finally omega square is equal to 2c m1 plus m2 divided by m1 m2 plus or minus 2c m1 minus m2 divided by m1 m2. So here also we have two values for omega square corresponding to this plus term and the negative term. Okay, so therefore omega square is equal to 2c m1 plus m2 divided by m1 m2 plus 2c m1 minus m2 divided by m1 m. So this will be, okay, there is this divided by 2 term is there. So 2c m1 by m1 m2 it will become, which is equal to 2c divided by m2. Okay, therefore omega is equal to 2c divided by m2 root of this thing. Okay. So this is this corresponding to the plus term. So this is called optical branch. Okay, so this value is omega, the omega value or omega square is 2c by m2, so which is corresponding to the optical branch at the boundary of the Brillouin zone. Okay, similarly omega square corresponding to this negative term, so 2c m1 plus m2 divided by m1 m2 minus 2c m1 minus m2 divided by m1 m2. So this will become 2c m2 divided by m1 m2, which is equal to 2c divided by m1. Okay, omega is equal to root of 2c divided by m1. Okay, so this is called acoustic branch. Okay, so these two are at k is equal to plus or minus pi by a. So we have seen the limiting cases of frequency at k equal to 0 and or k is very small and k is maximum. Okay, so here the intermediate value of omega square is found from this equation. Okay, now we can plot the graph of omega. In the x-axis we have propagation vector k or the wave vector k, and in the y-axis we can take omega, not omega square, omega. Okay, when k is 0, k tends to 0, we have neglected this term. That means k is 0. At k equal to 0, this term will be neglected. Therefore, omega square is equal to 2c 1 by m1 plus 1 by m2. Okay, so that is the optical branch. And acoustic branch, acoustic branch, omega square is equal to, when k equal to 0, omega square also 0. As k increases, omega square increases linearly. Okay, omega increases linearly. Therefore, so this is the value of omega when k equal to 0, and this is for acoustic branch. This is for optical branch. Now at the plus pi by a. Okay, plus pi by a. Minus pi by a can be taken here. Negative of this thing also we can plot. Okay. At plus pi by a, the value of acoustic branch will become 2c divided by m1. Okay, which is smaller value compared to a frequency corresponding to optical branch. Okay, so at the smaller value of k, as k increases, omega square increases linearly, and it will become 2c divided by m1 at pi by a. And this value actually the value of omega square for the optical branch actually reduces as k increases. This negative sign, the value of frequency decreases. Okay, so this is at pi by a. This is root of 2c by m1, and this frequency is root of 2c by m2. Okay, where here we have considered m1 is greater than m2. The mass of the first atom is greater than mass of the second atom. Okay, so this is the frequency versus omega versus k graph for a diatomic molecule. The frequency between these two limiting values is not allowed in the case of crystals of diatomic basis. Now let us see the transverse acoustic and transverse optical mode, how the vibrations occur. Omega square is equal to, first let us take the optical mode. Okay, omega square is equal to 2c 1 by m1 plus 1 by m2. So this is the optical mode. Okay, if we go back to the equation number 3 and 4. Okay, so this equation 3, we can write omega square minus omega square m1u is equal to cv 1 plus exponential minus ika minus 2cu. Okay, so in this equation, if you substitute the value of omega square for the optical mode, so you can write minus omega square is 2c 1 by m1 plus 1 by m2 minus omega square m1u is equal to c v into 1 plus exponential minus ika minus 2c u. So in this expression, if k is equal to 0, so if k equal to 0, what happens? This will be minus 2c, so this will be minus 2cu minus 2c m1 by m2 u is equal to, when k equal to 0, this exponential 0, that is, this will become 1. So 1 plus 1 is 2. This is 2cv minus 2cu. So this get cancelled. So finally what we are left with is u by v is equal to minus m2 divided by m1. Okay. So for a optical mode of vibration, u by v is equal to minus m2 by m1. So this u is the displacement of the first atom and v is the displacement of the second atom. So the ratio of these two is negative. That means the atoms vibrate against each other. So we can draw this graph like this. This first kind of atom, this first kind of atom. Okay. So the alternately arranged atoms. So they vibrate against each other. Okay. One goes up, the other goes down, but their center of mass remains fixed. Now if we substitute the value of omega square corresponding to the acoustic mode in the equation number 3, then we can write when k equal to 0, what happens? When k equal to 0, this entire term will become 0. This will be exponential 0 is 1. So we can write 0 is equal to Cv into 2. Okay, 1 plus 1. So 2 Cv minus 2 Cu. Okay. So from this we can write U equal to V. So that means when at k equal to 0, corresponding to the acoustic mode, both the atoms vibrate together. Atoms move together, that is. So we can plot the vibration here. This is the first kind of atom, alternately the second kind of atom, the first kind of atom. So both the atoms move together. So this is corresponding to the acoustic mode. So this is the propagation direction k. K is in this direction. The vibration is perpendicular to that. So this is a transverse acoustic. This is transverse optical mode. If the two atoms having opposite charges, then motion of this kind can be excited by the electromagnetic wave of frequency of light. Okay. So that's why it is called optical mode. And this kind of motion is excited by acoustic waves. And this kind of motion is similar to that of the acoustical vibrations. Okay. So that's why it's called acoustic transverse acoustic mode. Okay. So we have discussed the relation between the frequency and the wave vector k. So that is the dispersion relation in the case of crystals with a diatomic basis. And we have seen the limiting cases of this frequency at k equal to 0 as well as, or k is very small, as well as largest value of k, which is equal to plus or minus pi by a. Okay, so we plotted the graph and we discussed the vibrations in these two cases, vibration of transverse wave in both optical and acoustic mode. Okay,